Hi, and welcome to part 2 of Understanding SWR. I've got 3 things I've got to mention before I start. First of all, the weather has changed in Texas again. My allergies are acting up. My voice isn't the greatest. If my voice disappears from time to time, it's because I've muted the mic and I'm coughing my head off. So please, if you would, make some allowances for what might not be a stellar video after all. This series will be 4 parts. I'm trying to keep them to a half hour or less. Explaining basic SWR I thought could be done quicker, but I'm walking a fine line between accuracy and brevity, so I think the best I can do is 4 half-hour episodes. Now, one last thing. Some of the material I'm about to present is somewhat counterintuitive. When things start happening in an RF network, it's kind of hard to keep track of what's going on. So some of what I say is going to sound somewhat strange, and you might get the idea that I'm not describing things accurately. To that end, I will be doing lab experiments live in parts 3 and 4 to show you that this isn't all theory, that it's reality as well. In the last video, we talked about SWR, which is standing wave ratio, and we defined how it is a ratio between the forward and reflected power flowing down the line as representative of a waveform, or a voltage form. I talked about the book formula and how I like to look at voltages over using the power formula. And why? Because looking at voltages gives me a better picture of what's going on. Now, we talked about sine waves and frequencies. If you're not up to speed on those 2 topics, you can see on the screen I have another presentation that really addresses that a lot better. I'm going to answer questions 1 through 3 and 5 in this video. Number 4 is going to wait until next time, and actually the SWR meter calibration will be probably the first lab that we do. Let's go back to our lossless feed line again. Now, we already talked about having a lossless feed line. So in this case, let's give it some loss, 3 dB, which is it's a fair number. In many tower site installations where you have an antenna 300 feet up the tower, a 3 dB line loss is really not that unusual. So let's just call it 3 dB. Except in this case, we have 11.11% reflected power. That's giving us a 2-to-1 SWR. No different from other times, I suppose. Except now, that reflected power has to endure the loss of the feed line. When it gets to the transmitter, it's only 2.7775 watts, which is exactly mathematically half of 5.555 watts. So what's the SWR at the transmitter? It can't be 2-to-1. So we plug on the right our reflected power of 2.7775 watts into our formula, come up with an 11.785 voltage. We build this thing again. We assign the valleys and the peaks, just as before. We do the math, just as before. It comes up with 1.4-to-1. So, having a lossy line makes things look better at the transmitter than they really are. This isn't a good thing, and it isn't a bad thing. It's just the way things work. Now, one way it's good is perhaps our transmitter like many solid-state modern transmitters, doesn't like SWR. Perhaps it starts folding power back at 2 to 1. If we didn't have the line loss, the transmit power would start folding back anyway. So if the transmit power folded back 50% on a 2 to 1 SWR, we'd only be putting out 50 watts anyway. In that case, having a lossless line didn't get us anything. In this case, the transmitter is going to put out maximum power with much more SWR at the antenna than it normally would, because it doesn't see that SWR. Now, one little quick item, I won't leave it up for very long. I wanted you to see, just to make sure I'm making the point, SWR is greatly masked by line loss. Whatever my SWR is at the antenna, if I have line loss, I'm not going to see all of it at the transmitter. Again, not necessarily a good thing, not necessarily a bad thing. It just is, and we should be aware of it. So can a transmission line really be lossless? Actually, there are times it can, and in a few moments here, I'll show you an example of one. But if the line has loss, yes, it changes things. It doesn't change what's going on at the antenna, but it changes the ability for us to perceive that difficulty at the transmitter. Now, one last item for those that don't believe. If you don't really think power is flowing back to the transmitter, stick around for a few more minutes and I'll show you at least the concept and my personal experience. In the labs, we'll do a little more than that. In land mobile radio, we generally, in a fixed station location like a repeater or a trunked radio site, we don't allow reflected power to even get to the transmitter, but we make it look like the transmitter is absorbing it all. Let me show you how we do that. And then we can talk about every other case of reflected power where we don't take these measures. Here is your 2-meter ham repeater, or if you change the frequencies, maybe it's the local sheriff repeater. On the left, as I'm sure you can see, we have the transmitter and its frequency, 147.115. Receiver is 147.715. Now, all the cavities on the left pass the transmit frequency just fine. The cavities on the right only pass the receive. So when the transmitter power goes up the stack to the T, effectively, it doesn't see the leg going to the receive side. It only sees the antenna. The circuitry is very clever in that it causes, at that frequency, that T to look like an L, and it looks like there's nothing on the right. When the receive signal comes down the line, the opposite happens. It sees the green path, but the blue path looks like an open circuit, like it's not even there. So here comes our reflected power in red. And again, it doesn't even perceive that the green path is available. Problem is, now we've got reflected power going into the transmitter. We don't want that. The fix in this case is easy. We add an isolator. Now our problem is resolved, or is solved. There is no problem. Yeah, we still have a little reflected power, but the transmitter doesn't know it. So what's an isolator? Well, we start with the circulator. The circulator is just a very neat device. The mathematics and theory behind it are very intense. I admit I'm not up to speed on it. To me, it is almost completely a black box that does magic. You see, this thing is an RF roundabout. You must go around it in one direction only. And unlike the roundabout in your area, whatever port you come in, you must take the next exit. So during transmit, power comes in, the input port, goes out the output port. No problem. The loss in this thing is just incredibly small. So don't ask how many watts of power it wastes. They are very efficient. Again, I told you they were magic. Well, this is a circulator. What we need is an isolator. Especially once reflected power starts to come down the line. Here's our reflected power coming in. It has to obey the same rule. Take the roundabout in the right direction, get off at the first port. So how does this help us? Well, we take our circulator and we made it with a dummy load and we call it an isolator. Now, any reflected power coming down the line is going to go into that dummy load. So let's put it on our repeater. Okay, we got it on our repeater. Good. Now, if everything's working fine, you can key the transmitter and everything works fine, nothing happens. But if you don't believe that reflected power is real power, here's how you can convince yourself. You put an isolator on your repeater, you walk over and you place your hand on the dummy load. You instruct a friend to key the transmitter. You wait with the transmitter keyed 5 minutes. You'll notice that the dummy load doesn't really get warm. Now you tell another friend, disconnect the antenna while the transmitter is keyed. Then you observe how long it takes for the dummy load, because now it's absorbing all that power. You observe how long it takes for the dummy load to burn your hand. Once it burns your hand, you are now convinced that reflected power is real power. Okay, so I've answered the first 3 questions. I think we can go on to question 5. I'm sure most of you agree. Some of you probably object because I didn't talk about what you can do if you don't have an isolator. In fact, you just learned that if I put an isolator on my radio, all my received signals come down the line and go into the dummy load. So if I put an isolator on my radio, I can't hear anybody. So what do I do if I have reflected power on my radio? Well, then you have reflected power hitting your transmit port, because your transmit port and your receive port are the same port. So let's just consider for a moment the new repeater you're going to put up. It's a 100-watt transmitter, 3 dB line loss. You send a tower crew up with a dummy load and a watt meter. You run the line, you put the repeater in. You haven't hung the antenna yet. You verify you have 50 watts at the top, so you know your feed line's good. It's losing 3 dB. You're not mad about that. Seems like everything's fine. So you connect the antenna. You tell the tower crew, hook up the antenna and give me a watt meter reading. I want to know what you have. Well, they report 25% reflected power, or if they have an SWR bridge, a 3-to-1 SWR. Why would a brand new antenna reflect power? Well, in this case, you're mistreating the antenna, because the store that sent the antenna sent the wrong antenna. This antenna doesn't cover your band. Antenna is for a different band, so it's not going to work. Well, it's been a long day. So you have the tower crew come, put everything together, come down, and you go to lunch and just decide you're going to wait for the delivery of the new antenna. Your friend comes over and says, hey, how's it going? And you say, oh, it's a nightmare. They sent us the wrong antenna. And we're kind of in a mess. The friend doesn't believe you. So while you're not watching, he goes into the tower shed, puts a watt meter on the line, and notices there's only 6¼ watts reflected. Or perhaps he put an SWR bridge on the line and he doesn't even know how much power. He just sees a 1.67 to 1 ratio. And he says, hey guys, you made a mistake. It's not that bad. Then you explain to him about reflected power and the effect cable loss has on it. And then you get into an argument with him and you decide to go get your calibrated watt meter and you put it on. And you find out that the transmitter now is putting out 1.5 watts extra. So you assume that your watt meter just isn't all that accurate, and you let it go. So with that thought in mind, why did the watt meter reading change? Think about the 10-meter radio you put in your car. You put it together, the cable on the antenna is only like 9 feet long. So at 10 meters, there's almost no loss. You have a 1-to-1 SWR, no reflected power. Everything is working so good. Then one day, you realize you can't talk to anybody. You put an SWR meter on the radio and see that it's a 7-to-1 SWR. Well, obviously you have a problem in the antenna. But you're not too sure about your SWR bridge, so you go grab a calibrated watt meter and you put that on it. You know right away that a 7-to-1 means that if you have 100 watts forward, you should have 56 reflected, because a 7-to-1 SWR is 56% reflected power. But that's not what you see. At the radio, you see 114 watts forward. Now, that can't be possible, because you know that radio cannot produce 114 watts. It's not possible. So what's happened? Well, notice something. Your transmit power went up 14 watts. What's 4 times 14? It's 56. That means 14 watts is 25% of 56 watts. A 25% reflected power is a 3-to-1 SWR. That means the RF coming down the line, seeing that transmitter or radio, is experiencing a 3-to-1 SWR. But you say, no, wait a minute. The radio is a 50 ohm radio. It's got a 50 ohm antenna jack on it. This should not happen. It should all go back into the radio's PA and dissipate as heat. The forward power can only be 100 watts. Well, in the old days of tube type radios, every time you started your transmitter up, you tuned it to the frequency you're on. The circuitry in the output circuit, when you tuned it, matched the impedance of the tube to the 50 ohm line. So when reflected power came down the line, it saw a 50 ohm load that internally was transformed to the tube impedance. So all the power went back into the tube and got dissipated as heat. But today, our radios don't work like that. The amplifier in our radio probably covers, in a 10-meter radio, probably covers 20 to 30 or 20 to 50 megahertz. But it's not necessarily 50 ohm all across that spectrum. In some spots, it's going to have a different impedance. That different impedance, away from 50 ohms, is where the reflection's coming from. And what that all means is what you saw at the repeater site, take another look. 1.5 watts is 25% of 6 watts, 3-to-1 SWR. Now you know your watt meter reading was actually accurate. But that power is not coming from the transmitter final. It's a reflection of the reflected power, so it's a reflection of a reflection. Now I know what you're thinking. You're thinking, man, this guy will say anything to get us to watch his videos. Well, as I said before, in my lab experiments, I will duplicate what we just saw, except not with 1.5 watts. I'll use more power than that. And I'll show you where power is going and that this really does happen. So, how much loss we have in the line plays a big role in the SWR, or reflected power. That is, in the reflected power, or SWR, that we see at the transmitter. Up at the antenna, we see the truth all the time. It's at the transmitter that the additional loss paints a gray picture for us. And severe reflected power amounts at the transmitter can cause our forward power reading to be somewhat confusing. I'm going to attack this question because it seems like the right time. Why don't I use the word SWR at work? For those of you who missed it, I spent 30-some years as a two-way or land mobile radio technician. I now work in product development at E.F. Johnson. So to answer the question, first of all, let me say at the outset, telling me you have 100 watts forward and 10 reflected, or telling me you have 10% reflected, versus telling me you have about a 2-to-1 SWR, you're telling me the same thing. And both ways of stating it are accurate, and neither one is right or wrong, and neither one is better than the other. My preference is strictly a personal thing. I was taught by an engineer many years ago that I was never to say SWR in his presence or to a customer. That seems a little harsh to me, but I worked for him, so I did what I was told. His position, and I really do somewhat agree with it. I understand his perspective. Maybe I don't completely agree. I totally understand what he was saying. Take a look at this. Now, if a 3-to-1 is 25% reflected, a 2-to-1 is only 11%. A 1.5 is 4%. But look at this. One lousy watt is a 1.222 to 1. That just seems deceptive to me. I know, we all know that really anything from 1.5 to 1 on down is really a good match. You're doing good. I prefer to know what percentage of power I have coming back. A directional watt meter can tell me that instantly. Oh, it looks 47 and I got 3 back. Well, I'm well under 10%. I'm happy. The only time I would be upset, like I said, if I've got a repeater on a 300-foot tower, I better not see hardly any reflected power, because whatever I see, reality is way worse. So I just tend to like forward and reflected more. But here's another thing. Let me show you this. This is my 50-year-old, well, actually, this is the watt meter I had 50 years ago as a beginning ham operator at age 14. I recently bought a brand new one that was sitting in a box for 50 years. It's a wonderful toy. There's a unique thing about this SWR meter. Not only is it what I used when I was a kid, notice the scale. You have an SWR scale matched to a percentage of reflected power scale. Many SWR meters don't show the percent reflected. If they did, I'd be more happy using them. I just like knowing the exact amount of power I've got coming back, because I know in my mind 2% which is a 1.329 SWR. 1.329 to 1 sounds a lot worse than 2%. So I like percentages more than SWRs. But let me state one more time, doesn't matter which one you use, and I don't think one's better than the other. I just have my preference, and that's all it is. I hope this has been worth your time. I hope you've enjoyed watching it as much as I've enjoyed making it. In episode 3, we'll talk about this thing called additional loss due to SWR. You'll find articles on this all the time that will tell you, yeah, but if you got a 2-to-1 SWR, you're also losing more in your cable. And the loss is really worse than what the SWR says. Okay, I will address that in the next 2 videos. That's another one of them, like the SWR versus forward and reflected. I have my opinions. I will present to you my case, what I think about additional loss due to SWR, and I'll let you make up your own mind. I will give you all the information I have. Am I saying there is no additional loss due to SWR? No, I didn't say that. But I disagree with a lot of the statements made. So far I can't find justification for some of the claims made about the additional loss and how terrible it is. I don't think it's all that terrible. We'll talk about that next time. Thanks for watching.